Let me see if I can still eject this. I just pulled this out yesterday, and then when I put it in, it was telling me it wasn't working right. All right, now let me explain a little bit. We're going to go quickly through the stuff that I think either the Newton homework assignments or the slides you can grasp on your own, so that I can get to this stuff. Formulas, compounds, starting to name, because there is some things you do need to memorize, a couple of things. You need to really commit to memory, or at least understanding. So I'm gonna move in that direction. So if you see me look at some slides and just kind of point out a couple things and say, come back and study this, that's why. We mentioned isoelectronic. We said that these are things, for example, aluminum. Look at aluminum right there. Just aluminum 13. So 1s2, 2s2. I'm going to get 13 electrons in here. There's 10. 3s2, 3p1. So how many valence electrons does aluminum have? 3. And it's in the 3a, if you look on your periodic table, it says 3a, it says 13 and 3a at the top. Its main group column number is 3a, and that corresponds to the number of valence electrons. It loses those electrons. So it has 13 protons. It loses 3 electrons. It loses those 3. That's what its tendency is. It's a metal. Its tendency is to lose 3 electrons and form what? What ion? A +3 ion, and it becomes isoelectronic with neon. All right? We covered that. Sorry here, some things are overlapping. All right, there's a group that I said to remember. There's a group to remember. There's a group to remember, and there's a group to remember. Sometimes the 1A is a Roman numeral A, at where you might see a periodic table. And sometimes people aren't that familiar with all the Roman numerals. But 1A, 2A, or 2A. Same thing. 84 elements are metals, tend to lose electrons, form positive ions. Way on over into here. The tin, lead are metals. All these are metals, tend to lose electrons and form positive ions. A very small number up in here are nonmetals. Up in this corner, the noble gases, I wouldn't call those metals or nonmetals. Some people would say they're nonmetals. They're over in this corner. But what is a nonmetal? A nonmetal is an element that tends to gain electrons and form negative ions. Noble gases don't do that. They don't have a tendency to gain or lose electrons. They're inert. They're unreactive. They don't respond to reaction with other elements or themselves. So I wouldn't call them nonmetals. Although some textbooks are a little bit loose. Finally, they get over in here and they say, well, the nonmetals are over here, the metals are over there. Well, yes, but I would stop at the halogens and just, these are in a class of their own. They don't react. You can make a compound, a xenon fluoride. Someone did that. They wrote their PhD thesis on it, xenon hexafluoride. They had to work at it to make that compound, but they made it. So they got a noble gas here, and a very, very reactive nonmetal. And they made xenon hexafluoride. There's probably a few other little elements there, but you have to work at it to make a compound. 17 are nonmetals. I'm sorry, these titles are slapping over top of each other. And then there's the metalloids. The metalloids are right on the periodic table I gave you, right where that little step down goes diagonally from boron to astatine. Boron to astatine right there are metalloids. What does that mean? If boron reacts with fluorine, it acts like a metal. If boron reacts with cesium, it acts like a nonmetal. Okay? It's not going to lose an electron to cesium. Cesium is going to lose the electron to boron if you put those two elements together. So that's what we mean by a metalloid. It depends on what they react with, how they behave. Okay, I'm gonna go through trends in the periodic table quickly. Yeah, I'd like you to be familiar with this. This is the one I want you to grasp the most. We'll talk briefly about what ionization energy, electron affinity is, and see the trend. You'll probably have to come back and look at these slides because I'm going to say this a little too fast. There's going to be some graphs. You're going to have to get your feet on the ground. But come back, look at it. I'm not, I'll be honest with you, but I told you this is the first semester we're using Newton. I have not done all these homework assignments. I've gone in and glanced at some. There's some that aren't published you'll never see because I looked at them and I said, nah, we're not going there. We don't need to go there. That's not included in this course. Or it's too hard to put the answers into Newton. So I've unpublished some. That doesn't mean you won't get some that, and second thought I might say, well, that's kind of, I wish that was better or whatever. So you're gonna bump into some stuff I haven't seen. I don't have time to do these 70 homework assignments. I mean, I will eventually as I continue using Newton. So, but we're introducing it, and I'm trying to keep up with it. Someone asked me if you see a zero in the homeworks, and you will see zeros as we get past the due dates, I will manually put in zeros. You can go back and do those homework assignments. Just know they're going to do you the best good to get them all done before the exam. All right? This is what the homework is all about, and the quizzes is getting you familiar with it. Okay, so let's look at the trend in atomic size. Now, Mark, I think we do need this off. I'm glad you're here, Mark. I'm glad you have your coffee. Mark's alert. I will take attendance before we leave. At least I hope to. All right. There's a bunch of verbiage here, but a picture is worth 1,000 words. Now, look at this picture. This layout. Now it's laid out like a periodic table. And what are we looking at? We're looking at the size of these atoms. And it doesn't have it down here, but I think this would be in angstroms. Now an angstrom is like 10 to the minus 8 centimeters. Okay, it's extremely small. How do they get this? Well, you just saw lithium, sodium, potassium, rubidium, they had this stuff. If we took this down to some imaging place here in San Antonio and said, do an x-ray of this. I want an x-ray of my lithium. Okay. I said, not your chest? No, my lithium. So they'd x-ray the lithium, and what they would get, they'd look at their x-ray plate, and they'd have these dots on the x-ray plate. What are the dots? It's the nucleus of these atoms. Wherever there's a nucleus, the X-ray is going to hit something. Where there isn't a nucleus, the X-ray isn't going to hit anything. It's going to go right through. And so then they would say, okay, that right there That's the radius of that atom. From there, halfway over to the next one is the radius, and let's say, okay, this is how big lithium is. Then do sodium, get another X-ray, and you see the dots are further apart. Sodium's bigger, potassium's bigger, cesium's bigger, okay? So that's what we're looking at. What is the size of the atom? So there's a nucleus right there, and it's surrounded with a cloud of electrons, and and those electrons keep that cesium atom from getting any closer to the next cesium atom. So that's how much space it carves out. So what's the trend? As you go from the top to the bottom, what's happening to the size of the atoms? Getting bigger. So you don't need, I'm talking about trends. You don't need to know any numbers here. You just need to know what is the trend, okay? What's the trend? And the trend is that atoms, the size of the elements increase as you go down the periodic table. Let's see if that's true over here with the halogens. Fluorine, chlorine, bromine, iodine. Getting bigger, right? Not as dramatically as the metals over there, but still getting bigger. Now we don't have the helium and all of those. It's kind of hard to get those and get an X-ray. They're all gases. All right, now that makes sense. This is atomic number 3, number 11, number 19. Atomic number is going up, size is going up. Does that sound intuitively obvious? Okay, well now let's look at this. Let's look across here. 11, 12, 13, 14, 15, 16, and this is chlorine, 17. Atomic number is going up. What's happening to size? It's getting smaller. So as you go across a period from left to right in the periodic table, the trend is that the elements, the atoms of the elements get smaller, decrease in size. That is not intuitively obvious. Higher atomic number, 17, much smaller than atomic number 11. Look, there's 11, there's 17. Okay? So that's a trend you have to kind of, I can't just say that size correlates with atomic number. You can't say that. You can say the size increases as you go down the periodic table, almost no matter where you do that. That's true. There's boron. Here we are, getting larger as you go down, but you're getting smaller as you go from left to right. Now notice there are a couple exceptions. We're getting smaller. Oh, manganese is big, and then iron starts getting smaller again. All right, so there are some exceptions. That's why we call these trends. All right, general trends. Okay, there's an explanation for this. I'm not sure I'm going to go into it. Newton may drive you into a homework assignment that explains. It has to do with the shielding of electrons shielding the nucleus. And, well, let me just say real quickly, what is common about all of those is that electrons are going into the third energy level. 3s1, 3s2, 3s1, 3p1, 3s2, 3p5, 3. The electrons are going into the third energy level. And what's happening? The atoms are getting smaller. Those electrons are shielding that nucleus. that positive charge that is holding the electrons. There's more protons going in there. We now have 17 protons in there, and we're still putting the electrons in the third energy level, which is closer to the nucleus. So what happens? Look at chlorine, look at potassium. 4s1, that's the first electron to go into the fourth energy level, and boom, the thing swells out. Big. Much bigger than chlorine. Why? Because you got that tiny little electron way out there in the fourth energy level, and all these other electrons shielding the nucleus of its charge, and that electron kind of, this is like the 12th child in the family. She gets away. I would have never been allowed to do that. And what's mom and dad say? Hey, there's 12 of you now. I can't handle all 12 of you. All right, families. Sorry. Cation size and anion size. Another picture. All I want you to do, don't compare this to that. Just compare that to that. There's a sodium atom. How big it is. There is a sodium ion. Lot smaller. This had a 3s1 electron, and that has lost it. It lost all the electrons in the third energy level. Boom, they're gone. So now everything's in the second energy level, and the sodium ion is a lot smaller than the sodium atom. Potassium ion, smaller than the potassium atom. Rubidium, smaller. Cesium, smaller than the cesium atom. So, to write under this slide, just simply, the cation is smaller. Now, a cation is a positive ion. Cation are smaller than the parent atom they came from. Always. Anions, negative ions. So put negative next to here. Anions are negative ions. Chlorine atom is smaller than the chloride ion. What has that done? That has gained an electron to become isoelectronic with what? With argon. So the anion is larger than the atom it was formed from. Always. And that's all I expect you to grasp in anions and cations. And just compare the ion to the atom it came from. Smaller for cations, larger for anions. Okay, and ionization energy and electron affinity, I will mention right now, and like I said, hopefully there's a Newton homework and some reading and that will give you a little more appreciation for this. But let's just say what it is. What is ionization energy? It's the amount of energy needed to remove an electron from an atom. So we're writing it here, energy plus a sodium atom is going to yield a sodium ion and an electron. That is a sodium ion. So ionization energy is the energy needed to convert it into an ion. How much energy does it take to convert it into an ion? That's ionization energy. So if the ionization energy is lower, it's easier to remove the electron. If the ionization energy is very high, it's hard to remove an electron. Okay, now let's look at this trend. They've got atomic number down here. So here's number 3. 1, 2, 3, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. All right, look where we are. We're going right across here. We're going across the periodic table from the left to the right. And this is ionization energy. 0, 1,000 kilojoules per mole. Don't worry about these units. Just that's more energy, or that is more energy than that. All right? So don't worry about how we're measuring the energy or anything. But this is increasing energy. This is increasing atomic number. We're going across the periodic table. So as we go across the periodic table, ionization energy increases. All right, we said lithium is a metal. It tends to lose electrons and form positive ions. That's its tendency. It takes some energy to do that, but look, this is at 500 kilojoules. This is above 1,500. So it takes 3 times more energy to get an electron to come off of fluorine than it does to take an electron off of lithium. And that makes sense. We said fluorine is a nonmetal, and its tendency isn't to lose electrons. Its tendency is to gain them. So can you get an electron off of fluorine? Yeah, but you have to really work at it. It takes a lot of energy to do that. All right, so we go across that third period, and then bam, we're down here now. Sodium. We're back in this family. And look at the 500 kilojoules. Potassium, a little less energy. Rubidium, a tiny little bit less. Cesium might be a little less. All right, these are ionization energies. So that trend starts again. Sodium up to argon. Sodium up to argon. Ionization energy increases. So ionization energy increases as you go across the periodic table. Electron affinity. If you take an atom and add an electron to it and form an anion, it will release some energy. It actually gives off some energy. And we call that energy electron affinity. The energy change when a single electron is added to an isolated atom. Large electron affinity indicates that an atom becomes more stable as it forms a negative ion. Okay, let's look at the trend in the periodic table and just see if it makes sense. Electron affinity, and notice here's let me make this bigger so we can see it better. Okay, so where are we? There's sodium, magnesium, and then we get what, to aluminum, silicon, phosphorus. What did we miss? Sulfur. Sulfur is not even in there somewhere. And chlorine. But so it does jump around. It's jumping around, electron affinity. But we're saying that if you add an electron to chlorine, you release quite a bit of energy. And adding an electron to sodium, you only get maybe 50 kilojoules per, but here you get 350, 330 or so. So these have a high affinity for electrons, and they show it. They show their appreciation by all this energy they release when they receive an electron. So electron affinity increases as you go across. Ionization energy increases as you go across. Just keep in mind that we're measuring two different things. And I think that's about, this summarizes these trends. Atomic size increases, going down. atomic size increases going across this way or decreases as you go from left to right. It decreases. And, okay. You may have questions. If you do, I can understand you have questions. Drive yourself into Newton to get some of those answered, or come and see me. I mean, you don't just have to do that, or ask me after class. I want to try to get us. Don't worry too much about that slide. It's talking about removing 1 electron, 2 electrons, 3 electrons. We don't need that level of detail. Oh no, 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 no. This came in in a way that didn't come in as individual slides. Why didn't it do that? Came in 2 slides at a time, I guess. All right. I'll blow them up. Okay. You ready to shift gears? Module 4. Exam 1 will cover modules 1, 2, 3, and 4. And it will be, I'll tell you more about exam 1. What is today? Tuesday. On Thursday, I will tell you a little bit more about exam 1 and when it will be, how it will be delivered, all of that. For right now, just know you need to be grasping modules 1, 2, 3, and 4. And we're going into an important one. I'm going to be handing out some worksheets that we will do a little bit in class. I'll be encouraging you to do these with one another. Go get together and start working on these. All right, so chemical bonding. Okay, this is an important milestone and crossing. We're crossing from talking about individual elements and atoms and their behavior to now start to talk about how they are reacting with one another. How does one element interact with another element to form a compound? And 99% or 95% of the stuff you see are compounds of one form or another. All kinds of compounds. The salt you put on your food is a compound. The sugar you put in your recipes is a compound. Sugar is a covalent compound. Salt is an ionic compound. What do we mean by that? Look at that. They're both white crystalline solids, right? Table sugar, table salt. You go, wow, they're both white. They're both solids. They're both soluble in water. But one is a covalent molecule, and the other one is sodium chloride ions. They're for different reasons, they're soluble in water. And they are different. One's sweet, one's salty. Right? So your taste buds react to them very differently. You know the difference between salt and sugar. Just like that. If someone puts salt in your sugar bowl, you put it in and you go, oh, what happened? Right? They're different. They look a lot alike. Okay, so chemical bonding. Chemical bonding, we're talking here just in general. There's not an element A or B up there. Just in general, if we had an element, call it A, plus element B, they react together, they form a compound, AB, of some sort. We're going to see this sort of thing, where you get A2B, or you get a different element. It might be AB2. They're going to be formulas. They don't always react one atom of one with one atom of another one. Remember Dalton? Dalton said compounds are the result of elements reacting with each other, and you always find them in small whole number ratios. So the ratio here is 1 to 1. The ratio over here is 2 to 1. And over here it's 1 to 2. That's what those numbers are telling us. A chemical bond forms. There's a chemical bond that now is binding A to B. And the nature of that bond can be two different kinds: ionic or covalent. Ionic is, that's the key word. Ionic bond, transfer of electrons from one atom, one element, to the other element. You're transferring electrons. You're making ions. Covalent bond, the operative word here is sharing. We're not forming ions. The two atoms in the bond are not transferring electrons between each other. They're sharing electrons between each other. For example, H2O is a covalent compound. It is held together by two covalent bonds, a hydrogen-oxygen covalent bond and another hydrogen-oxygen covalent bond. Hydrogen isn't an ion in water. Oxygen isn't an ion. They're sharing. So let's look at ionic. So here's an example. We already looked at this, and this is a Lewis dot structure here. All we're putting, and we'll look at this right now, we're just putting the valence electron. Sodium has 11 electrons around it, but it has a 3s1 valence electron. And in Lewis dot diagrams, the only dot we put in the symbol is the valence electrons, or the only dots. Sodium happens to have one. So it loses that one electron, and it forms a sodium plus one ion. So what happens? That electron is transferred to a chlorine atom, and it forms a chloride ion. Sodium will never do this all by itself. That's why in the video you saw, there was the sodium metal sitting underneath the oil, and it's sodium metal. It's got all its electrons. Why? It will not transfer that electron until it comes into contact with another element that's ready to receive that electron. Okay? A positive ion does not form just kind of all by itself. It very readily forms when it reacts. A metal reacts with a non-metal. You get a positive ion and a negative ion. And you form an ionic compound, sodium chloride. And what we understood in there is this has got a positive charge, this has got a negative charge. Chlorine doesn't exist all by itself as an individual atom floating around like helium would or neon. It is a diatomic element, Cl2. So there's the sodium metal, just like what you saw on the slide. And it's under oil. They got it under oil. There's chlorine. It's a yellow gas, poisonous. When I talk about chemistry in the news, there have been times, I haven't heard of any recently, but in the past 5 years it has occurred. In the past 15, 20 years it's occurred many times. They're transferring chlorine in a rail car, and the train is derailed, and the rail car is tipped over, and it's spilling out chlorine gas. Then they have to evacuate the area. because this is poisonous. This is a poisonous gas. Because it is so reactive. You breathe it in, it starts reacting with your lungs and doing damage to them. And sodium metal. Sodium metal. You can't swallow sodium metal. It'll burn going down your... So this is poisonous. That's poisonous. You react them together and you get table salt. Amazing? Amazing. And why is table salt not poisonous? It's not poisonous because it's done reacting. It's not going to react anymore. This sodium is happy next to the chloride ions. The chloride ions are happy next to the sodium ions. And you swallow them, they dissolve into sodium and chloride ions, and they don't hurt you. But the element will. All right, and so here is what sodium chloride looks like. Here's your, remember the sodium ions, the positive sodium ions, they get smaller. The cation gets smaller, the chloride ions gets larger, and that positive sodium ion is surrounded by, as it packs down into the sodium chloride crystal, it is surrounded by chloride ions. It doesn't want to get close to another sodium ion. Like charges repel. But there is a 1-to-1 ratio in this crystal structure. All right? And every negative ion has 6 positive ions around it. Every positive ion has 6 negative ions around it. Just the way they pack in there. Very naturally. Boom. Because of the like charges. See, here's the sodium atom here, big, becoming a small sodium ion, and here is the chloride atom getting larger as the electron is transferred. This is the electron being transferred in this direction to the chloride. And it's an ionic compound. Hydrogen. Hydrogen is diatomic, but we don't see a hydrogen atom transfer an electron to the other hydrogen atom. They both want another electron. And so they share them. They share the electrons. And they form this, they're just showing the orbitals where these electrons are, and now you have a molecular orbital and you have a hydrogen molecule. So the 2 shared electrons we're converting those 2 dots into a line. This is a single bond. This is a single covalent bond made up of 2 electrons. Now let's see, did I skip over the Lewis dot diagram? Yeah, I did. I'm sorry. I skipped over an important slide back here. I hope I'm not jumping around too much and losing you. You with me? You can jump around? You're multitaskers? Okay. All right. See, a minute ago, I wrote sodium this way. And what did I say? I said we're only going to put the valence electron in this symbol. Now remember, the alkali metals all end with an S1 electronic configuration. That means they all have how many valence electrons? 1 valence electron. So in a Lewis dot diagram for these elements, all you do is change the symbol and put 1 dot next to it. They all have the same Lewis dot structure. See, this is, let me see if I can make it much bigger. All right, so we got lithium with a dot, sodium with a dot, potassium with a dot. representing that one valence electron. How did that happen? What happened? I don't even know what I touched. There we go. Okay, now look at the alkaline earth. I'm sorry these came in here as two at a time. I know there's a way to avoid that, but why it did. These all end in S2. You know, 3s2, 4s2, 5s2, 6s2, 7s2, so they have 2 dots. Aluminum we saw a minute ago was 3s1, or excuse me, 3s2, 3p1. These are S2p5 configurations. S2p5 configuration. So they have 7 valence electrons right here. S2p5 right here. So they have 7 dots. All right? And when we put those, don't do it this way. Don't just go 1, 2, 3, 4, 5, 6, 7. Don't just randomly put the dots around there. The better way to do it is to do it like this. So imagine you got a little box around these. And what you're doing is you're putting pairs of electrons 2, 4, 6, 7 like that. It doesn't matter. It doesn't matter to me if you did it like this. You can kind of put that single dot wherever you want to, top, bottom, middle, or not middle, but top, bottom, either side. But with that kind of pattern, 3 sets of 2 and a unpaired electron right there. Okay, why are we doing it that way, particularly over in here? Well, let's take a look at neon. Remember, neon was 1s2, 2s2, 2p6. It has 8 electrons. That's what we got right here. Except for helium, it only has 2. But neon, argon, krypton, they all have the same kind of symbol with 8. Remember, 8 is an octet, right? Remember the octet rule? Elements are going to behave in such a way to achieve the electronic configuration of the nearest noble gas. So I can look at this neon, I can look at fluorine, and I could just look at it and I visually see what fluorine wants to do. Fluorine wants to get an electron right there, to get an octet. That's easier to see than if I just randomly throw those dots around there. You see why I'm saying that? And then oxygen, look at oxygen. It has 6 valence electrons. I usually do it like that. The chart there put 1 set above, 1 set below, and 2 dots on either side. And just quickly to show you why I do that, what happens? You can look at this and you say, well, the oxygen would like another electron right there and another electron right there to get an octet. And how does it do that? To use something you're very familiar with, what's the electron configuration of hydrogen? That's it, right there. It's got 1 electron. And it wants to be like helium. That's its nearest noble gas. And what's the electronic configuration of helium? Right there. Hydrogen wants to be like helium. Hydrogen is not going to get an octet. It only has 1 proton in the nucleus. There's no way it's going to attract 8 electrons to it. Helium, same way. It only has 2 protons in the nucleus. It's not going to attract, but it gets 2 electrons and it fills the first energy level. That's why it's like neon and argon and krypton. It has filled an energy level. And then neon, argon, and that, they're getting that octet. So then we really write this way. That's our H2O. That's our favorite drink. You might say, no, that's not my favorite drink. I like lattes, I like this, whatever you like. That is your favorite drink. This is what's keeping you alive, folks. Water. All right, where are we going? So I need to get you started. Let me see where we are and get some things in your hands. So let's get back to ionic. I'm going to drift away. I'll try to come back to these. Remind me to come back to these slides. This is talking about covalent. All right, now we're back into bonding. We're going to have to understand electronegativity. I'll make some notes to myself. And let's get into, and we'll come back and go over electronegativity and all that, but let's start looking at nomenclature for ionic compounds. Sodium forms a +1 ion. Chlorine forms a -1 ion. It is going to form a compound that is neutral. The compound has to be neutral. And no matter what compound you buy from you can buy 1,000 organic compounds. They're going to come in a bottle. The bottle's going to be neutral. There's going to be an equal number of positive and negative ions in the bottle. Positive and negative charges. Not positive and negative ions, but the total positive charge is going to equal the total negative charge. So one of these goes together with one of those, a +1 plus a -1 is neutral. That is why this is a 1-to-1 ratio. So let's take a look, and this is called sodium chloride. It's not called sodium chlorine, it's called sodium chloride. To a chemist, chlorine is Cl2. It's the element. Chloride is Cl with a -1 charge. It's the chlorine that has been converted to an ion, and we call it the chloride ion. Sodium, we don't change it. It's sodium metal. When it becomes an ion, we just call it a sodium ion. Okay, now let's take a look at magnesium for a minute. Let's look at a compound called magnesium chloride. What charge will magnesium have on it? And take a look at it. It's atomic number 12. It has an S2 ending +2. It's going to lose those 2 valence electrons. That's what magnesium wants to do to become like neon. It has to lose 2 electrons. So it ends up with a +2 charge. Chloride doesn't decide to receive 2 electrons because it's reacting with magnesium. It only wants 1 electron. Follow me? It doesn't change that desire just because now it's reacting with magnesium. It shows a -1 charge. So if we put these together in a 1-to-1 ratio, it's not going to be neutral, is it? +2 -1, it would be a +1. Magnesium chloride is not positive, it's neutral. So if we take that number, transfer it right there, and we take that number and transfer it right there, we get MgCl2. And now we have a plus 2 ion, but we only have one of them, times 1. Plus we have a -1 ion, but we got 2 of them. So this is plus 2 plus -2 is neutral. You follow me? So the formula for magnesium chloride is MgCl2. Okay, now so right now think about this. You figure out aluminum chloride. Aluminum chloride. What do you think the formula should be of aluminum chloride? Given what aluminum would do, how it would behave, and what chloride does. Find out where aluminum is. How many valence electrons does it have? Guess the formula for aluminum chloride. AlCl3. Everybody get one of these? Agreed? AlCl3? All right, so that's driving off of the fact that aluminum would have a +3 charge. So it's aluminum with a +3 charge. It has 3 valence electrons. Chloride is going to have a -1 charge. We're going to move this 3 right to there and that 1 there. Not the -1, just the 1. Just the magnitude of that number. And we get an Al1Cl3, but we do not write 1s in these formulas. Okay? 1s are understood. Okay, so let's see if I think I have these slides coming up. Yeah, here we go. Now I've just given you a paper with 4 slides. I think it's the next 3 or 4 or 5 slides here have these. You should start getting very familiar with them. Start with this first slide. Right here. This is what to start with. Because what you're seeing, over and over again, we worked with a chloride -1 ion, didn't we? We didn't change that. Sodium chloride, -1. Magnesium chloride, chloride's -1. Aluminum chloride, chloride's -1. And the charge on the chloride drove us to figure out how many chlorides need to go with this positive ion, right? Okay, so knowing the charge of some of these key elements right here that are very, very predictable, that's what you have on this first slide. You're having, now notice here, lithium, sodium, potassium, rubidium, cesium, francium are all going to be +1. This is group 1A right here. And it could go right down. We just went lithium, sodium, potassium, rubidium, cesium, and francium, same thing. So just think, plus 1. Right here, we have 2A. Magnesium, calcium, barium. Magnesium, calcium, barium. We skipped over strontium and radium. But those are all, and beryllium, those are all plus 2 ions. Notice back here, that's what this was getting at. You learn it however you want to learn it. Just learn it. These are very predictable, plus 1 ions. Very predictable, plus 2 ions. The halogens, very predictable, minus 1. Fluorine is always going to be minus 1. Almost no matter where you see it, it's a minus 1. Chlorine, bromine, iodine. And then you got oxygen and sulfur, and then you have nitrogen and phosphorus, and that's what I have. That's what I have here. So by Monday, or no, I mean by Thursday, learn that chart. Let's see. I don't know if I can get to it. Can you? Some of you got 9:30 classes. A long way away? Okay, Pecan Hall. All I want to mention, let me just tell you, on Canvas, let me just tell it to you rather than trying to bring it up. You're going to see a naming and formulas practice quiz. So now what you have to do is you got to go down here to the tab that says quiz. When you go to your student page, go to quiz, you're going to see that. There's about 200 questions in there. It will randomly pick 20 and let you do the quiz. By Thursday, just find out where that is. When we come in Thursday, I'll pull one up and we'll start trying to do a quiz. You can do it over and over and over again, but what I want to tell you is that next week, I'm going to put that exact same quiz over in the testing center, and you have to take it. It's going to randomly pull questions. Nothing's going to change about it, except that one's going to be graded. So if you want to take that one 20 times until you get a 19 out of 20, and then run over there and say, I'm going to get at least 19 out of 20 on this thing, you can do it. And I'm going to leave that quiz open until the final exam, that practice quiz. You can practice this all you want to learn how to name, and I haven't taught you enough to name everything that you will get thrown at you. But by Thursday, we'll get there. All right? So start working on that chart. Commit all that. Understand that. I'll see you Thursday.